Hello, welcome to the next part of design of the STATCOM. In the previous STATCOM video, we designed the power circuit and measurement circuit. Here we have added the voltage source inverter, which is IGBT based. Now we have to design the gate pulse, that is a controller circuit for this. So for making the controller circuit, we are using the instantaneous PQ theory. Take the VL and IL measurement, convert into DQ0, then calculate the instantaneous power. We don't want to inject any active power because there is a capacitor only, so keep the active power 0 and reactive power is to be injected. From that, calculated the compensating current. From that compensating current, reference current is generated. Reference current is compared with the actual compensating current in hysteresis controller, and then gate pulse is designed. So let us begin with the from block. So take the from block. In this from block, I will change this is to VL. Now take this similarly. Okay, so let me zoom somewhat so we can able to design this properly. Okay, so here we have a VL. Take the block same. Then here it is a IL. First we need the PLL block. So go to the PLL, three-phase PLL, because we want to take the information of omega t. So connect the VL to this VABC to VL. Then take the block of go to. Wait. Go to block. You connect this go to block here. Okay. Now this block is of omega t. Rename with omega t. Make this variable as a global variable. Apply. Okay. This omega t we require for further calculation of ABC to DQ0. Then take the block of ABC to DQ0. Connect this ABC to DQ0 to the VL block. Then copy this same ABC to DQ0. Here I need a from block. Connect. This is here, which is equal to omega t. The same omega t we want at this block, so you can either connect a separate go to block from block, or you can connect with this omega t. Now here what is available, VL dq0 and IL dq0. From this we have to calculate the power. So let's take a block of power measurement. In this power measurement, take the block of power dq0 instantaneous measurement. Okay, so here we will get connect the VDQ0, IDQ0. Here we'll get the load side active and reactive power. Okay, in this case we'll get the load side active and reactive power. We have keep this in the power variant mode. So after this we want to calculate the compensating current. So to calculate the compensating current, instantaneous peak from the instantaneous PQ theory, take the block of MATLAB function. This MATLAB function you can do the programming inside the your simulation. So double click and open the MATLAB function. Okay, what I want into this MATLAB function, I want the compensating current ICD, then ICQ, and then IC0. These compensating currents are the functions of VD, VQ, V0, ID, or V0 is not required actually, ID, IQ, and again I need a PQ also, so I will give this name PQ in between, PQ. Okay, ID, IQ, and I need I0 also. Okay, so I0. So now you can observe in this, this compensating current are the function of these 7 values. So how, if we go in upside, so you can check the block. So here I will get a compensating current. So I need what first VD, VQ, and in the first block. So take a block of demux. In this demux, set number of outputs are equal to 3 because there is VD, VQ, and V0. Connect at the output of VD, VQ, V0. Connect VD to VD, VQ to VQ. V0 we don't need actually here. Then copy the same demux here. Then you connect it to power measure current ID, IQ, I0. Then connect this ID, connect this IQ, connect this I0 here. So ID, IQ, and I0 are connected. Now, what I need the reactive power is to be compensated, but the active power compensation I don't need into this. So, so that I want to set the active power is equal to 0. So take the block of constant. In this constant, make this constant is equal to 0 and connect this block to the P. So it will not inject any active power. Now how to design the IC, D, ICQ, and IC0? For this, these are the formulas which are given here. ICD is equal to 2/3 VDP plus VQQ, VD square plus VQ square. Similarly, same formula is here, but VQ is here, VD is here, and minus sign is there for ICQ. And IC0, sorry, this is not ICQ, this is IC0. IC0 is equal to IL0. So please make this note, this is not ICQ, this is IC0 last term. So we'll design this these formulas. Now I want to calculate the ICD. So what is the value of ICD? ICD is equal to 2/3 into 1 upon VD square plus VQ square multiplied with VD into P plus VQ into Q. Okay, this is the ICD. Next, ICQ. I will get the ICQ. The formula will remain same, but here instead of VD, first it is a VQ, then sign is, sorry, first is a VQ, then sign must be minus, and this sign must be, this is must be VD. So this is the VCQ, ICQ. Now we will calculate the IC0. IC0 is equal to I0. Okay, so it is not anything, it is just only I0. So I will put the semicolon at each end. So now I will get the compensating current. Okay, so now I want to design the hysteresis controller for uh, gate. Gate. So how to design this hysteresis controller? I have designed this already to reduce the time of video. I will take that from my previous slide. Okay, so let me take this in my video. So I will explain that how pulses are generated. Okay, so now double click to this. Here IC, ICB, ICA, ICB and ICC is required, which is compared with the actual compensating current. Here we have a hysteresis block. In this hysteresis block, switching point is 0.01, 0.01. Output is 1. Okay, so likewise hysteresis band. So this is a relay. Use the relay function to design hysteresis band. Not signal of this is connected to the bottom of second. So why we need a convert? Okay, so we want this output in terms of real world value as a floor. So we need a convert block, because not block will give you the binary value. The binary value must be converted into the floor value, so that it is convert block is added, data type conversion block is added. So in this block we need ICA, ICB and IC, but here it is ID, ICD, ICQ and IC0. Next, so we'll need DQ0 to ABC transformation. In this DQ0 to ABC transformation, I will connect the block of mux first. I will set this number of inputs is equal to 3. Okay, connect ICQ, ICD and IC0. Okay, connect this block here. Okay, what I need from this, omega t is required, so take the block of from, connect this from block here, because omega t is already measured in PLL, so still I need to set the PLL value. Okay, so I have not set the PLL, so come to the PLL block. This is your PLL block. In this PLL block, minimum frequency is 50 Hertz. Initial output, keep this is to 50 Hertz, because our frequency of the system is at 50 Hertz. Make this change, and cutoff frequency you keep it to the 5 Hertz. Cutoff frequency, you filter cutoff frequency, you keep this to the 5 Hertz. Okay, so change like this. Now omega t you will get from here. This omega t here you will get ICA, ICB and ICC. So what I will do, I will change again. I will take the demux block here. Make this number of inputs are equal to 3. Outputs are equal to 3. Connect ABC block here and IA, IB and IC. Okay, here in this fourth block, what I need, okay, I will rename this fourth block. Okay, in this fourth port, I have to give the actual compensating current, that is IC. So then this name will be reflect here. Connect the block of from, connect this IC block over here, that is actual compensating current fed by the STATCOM. Okay, so where is this IC block is here in this system. If you come here, here we have added the VI measurement block. In this name was given IC. This current was name was given in IC in the previous video. So look carefully the previous video. So we have designed the power circuit and control circuit. Whatever the signal you are getting at this, these are the pulses. So now connect the block of go to, connect this block here, total 6 pulses. So this is the phase A bottom phase, phase B bottom phase C bottom phase. Okay, so these are the total 6 pulses are generated. Name this as the gate, make it global. The spell of gate must write down clearly as we have written here. Okay, gate. Okay, so this is connected to this gate block. Now everything is over. Just I want to add the again in the measurement block. Come to the measurement block. In this measurement block, we have to add two more measurement. Okay, take the block of from. Here I need compensating voltage VC. Let me move this my all downside, and I need one more. Here it is IC. Okay, then come to the take one more scope instead of adding in that scope, because while taking the printout it may create a problem. So click on the scope, double click, open the scope parameter. Here give the scope parameter is equal to 2. Layout I will choose vertical. Okay, apply. Okay, then you connect this block here. Okay, this block here, you can rename this as STATCOM current, and this as STATCOM voltage. STATCOM current and STATCOM voltage. Now what I will do, I want to measure the power factor of the same. So you can extend this block further. You copy this entire thing. Here change this name as VC. So it will measure the power factor of compensator. Obviously, power factor of compensator must be near to 0 because it injects only reactive power. So let's check what will happen. Okay, so let me rearrange the circuit. So this is my controller circuit. Can add the controller in one area. Rename this with controller. Now everything is ready. Let's simulate the circuit. Let's run the circuit. Circuit is simulating, it's compiling. First time may take the time to compile this. It's initializing. Now it's a running status. Okay, now come to the power factor block. See, you can observe here the source current is now at unity power factor. Load current is having the original power factor 0.64, whereas your compensating current is almost having the 0 power factor. It's injecting the reactive power. So come to the VS and IS block. So you can observe here, if you zoom this window, you can observe here the current and voltage are in phase. This current and voltage are in phase, whereas in load side current and voltage are having the phase angle difference. Current is lagging to the load voltage. Okay, you can check these things with the what you can say, the leading type of power factor also, because it should behave on the leading type of power factor also. So okay, let's check with the leading type of power factor. Okay, this first simulation is over. So you can observe the voltage and current are in phase. So coming to the this side, instead of this power, I will make the reactive power is 12,000 VAR. And once again run this circuit. Okay, still the power factor will remain 0.64, but the current is leading in this case. So you can observe load side current is leading. So let me zoom this much window. Okay, see, this is the voltage waveform. Voltage is zero at this stage. The red current is leading to this. So current is leading, but in this side, if you observe, all currents are in phase. Okay, all voltage and current are in phase. If you look to the compensator currents, compensating current will be 90-degree leading, 90-degree lagging. So let's check compensating current. Okay, see, this voltage is this voltage, you can observe this is going negative side from here, but it is early side on negative. So you can observe the capacitive, it's working in a capacitive mode, injecting, absorbing the current. So this is what we expect from this. Power factor is still unity. Power factor is still unity. So it's working in STATCOM as a reactive power compensator. You design this circuit in the MATLAB and tell me the comments on my YouTube video. Thank you very much.